Hi folks, we're going to take a look at number 10 from page 146. So I'll read out the question. It says, determine the area of the largest rectangle that can be inscribed inside a semicircle with radius 10. Place the length of the rectangle along the diameter. Okay, so here we have a geometry problem, and in order to be able to apply some formulas, I'm going to turn it into an analytic geometry problem. So we've got a semicircle, which I'm going to place so that the center is at 0, 0. Okay, so here is a semicircle, and it's got a radius of 10, so it's going to go from 10 to negative 10 on the left, and we're inscribing a rectangle somewhere in here, okay, so that the base is along the diameter. Okay, so here, notice a little trick that we've used before is wherever the edge of this rectangle is, let's call that x. Okay, and then we know that we're going to have negative x on the other side, so the length of this rectangle can just be given by 2x. Then we realize that the height of the rectangle is just the function value of that circle at this x. Okay, so we're going to need a formula for this circle. Okay, so let's remember the equation of a circle centered at the origin is x squared plus y squared equals the radius squared. Okay, and here let's solve for y. So y is equal to the square root of 100, 10 squared, minus x squared. Now normally we'd be taking the positive and negative square root, but we only want the top half of the circle. So we only want those positive y values. So that's why it's just the positive square root. If I wanted the bottom half, I'd be taking the negative square root, the negative y values. Okay, and now from here I can come up with a model for the area of this rectangle. Okay, so it's the length 2x times the width, which is just the y value of that function, 100 minus x squared. Okay, let's take a look at the domain of this function. So x, well, clearly has to be greater than 0, okay, and must be less than 10. It can't go beyond the edge of the circle and can't be actually equal to 10, otherwise we just have a straight line. Okay, so again here we see we don't have a closed interval. Okay, so now we have our model, we have our domain, now it's time to do the calculus. So let's take the derivative of this function here. So this 2 is just a constant, so I'll leave it out. So derivative of x is equal to 1 times the second function, so obviously I'm using the product rule. Okay, plus the first function x times the derivative of this here, so this is 100 minus x squared to the 1/2, so that's 1/2, 100 minus x squared to the negative 1/2, and times the derivative of 100 minus x squared, which is just negative 2x. Okay, so let's simplify this. So the 2 here remains. Here I've got the square root of 100 minus x squared. Here the 2 cancels out with that 2 in the numerator. So in the numerator here, the only thing I'm going to be left with is the x times negative x, which is minus x squared. And in the denominator, well, I'm going to have this 1 minus x squared to the 1/2, so square root of 100 minus x squared. Okay, so in order to solve this, let's bring everything to one denominator. So multiply, use root 1 minus x squared as the common denominator. So multiply to that here. I just have 100 minus x squared. Okay, and then here minus x squared all over the square root of 100 minus x squared. Okay, and when is this going to be equal to 0? Well, when this numerator is equal to 0. And we see that the numerator here is just negative 2x squared plus 100. Make that equal to 0, so we have 2x squared is equal to 100. X squared is equal to 50. Okay, and so x is equal to positive or negative root 50. Okay. Now again, since we need x to be positive, we're going to get rid of that. Now this is not, this is a purely geometric problem, so I'm going to expect exact answers here. Okay, and here, since 50 can be simplified, 50 is 2 times 25, so this is x is equal to 5 root 2. Okay, now we do have to test that this is indeed a maximum value. Okay, but here, since that's always positive and the 2 is always positive, I just have to look at the 100 minus 2x squared. Okay, and so here, let's test. We had, we're only interested in greater than 0, but we had 5 root 2 and negative 5 root 2, and here we see that it's a parabola opening downwards. Okay, so we see that the derivative is going from positive to negative. So we have a local max, but from 0 on, it's actually going to be the maximum. Okay, the absolute max just in this area, because here we see that it's continually increasing to 5 root 2, and then it keeps continually decreasing. Okay, so that'll give us the maximum value. Let's just check what they actually want. They actually want the area. So what we need to do is use the area function to determine the maximum area. So area is going to be 2 times x, which is 5 root 2, okay, times square root of 100 minus 5 root 2 squared. Okay, so let's simplify that. So here we have 10 root 2 times square root of 100 minus, so this is going to be 25 times 2 is 50. Okay, so 10 root 2 times square root of 50. But hey, we can just keep going here, because 10 root 2, okay, as we did before, root 50 can just be written as 5 root 2. Okay, so root 2 times root 2 is 4, times 5 is 20, times 10 is, looks like 200. Okay, oh sorry, root 2 times root 2 is root 4, so that's 2, times 5 is 10, times 10 is 100. Okay, so 100 units squared. Okay, and that's this one here.